applications of simulation in the evaluation of SCADA and ICS security. So the motivation for our work. Industrial control systems are highly target rich. So what that means is they can typically be large networks with multiple interacting parts. They can span large geographical areas, and they can have a very heterogeneous composition in the sense that there can be some legacy components, and there can be some new components, and there can be everywhere in between. So what you kind of get is this situation where you have some process logic controllers or PLCs that exist that might be vulnerable to cyber attack, and then some newer ones that maybe have the capabilities to prevent these attacks. But it's not an all or nothing type of scenario where you can just go in and replace everything with these new and highly updated pieces of technology just because these systems are large and it's expensive, right? So sometimes you don't want to mess with things that already exist, that already work. You don't want to break anything. Some people are opposed to bringing in these new technologies because they know what they have already operates pretty well, right? And then the other thing is that these systems, so industrial control and SCADA systems, they support critical infrastructures like gas pipelines, electrical grids, some manufacturing centers, and other kind of, like I've heard of military bases and other things kind of using these systems, right? And that makes them a desirable target for people like terrorists or nation states or foreign actors, the kind of people who would basically have a vested interest in either compromising these systems, causing harm, shutting them down, whatever. And so, as a result, right, we want to be able to defend these systems. Well, testing industrial control systems, especially gas pipelines and electrical grids, testing them for safety is a common thing, and that has been something that's been done for a long time. It's been researched, right, because the ultimate goal is the people who work at these, whether they're power plants or, gas compressors or whatever, those workers need to be able to do their job safely without getting hurt. And these systems, almost equally as importantly, need to maintain availability. And what that means is that, you can't have the power going on and off intermittently or gas going on and off intermittently. These systems need to maintain their availability, right? But the issue is that safety processes like the ones that have been developed haven't really been fully refined to deal with the kind of plethora of cyber attacks that are coming in this kind of new world, right? As these systems start to either become more connected to the internet, whether it's through corporate networks that are connected to these SCADA systems, or whether it's through maintenance workers whose laptops they bring to work and they're on the internet the night before and then they go into work or whatever. There's ways that these systems can be compromised, right? So we need to find ways to test cybersecurity on these systems. And the issue is that testing on live versions of these systems can be extremely dangerous, it can be expensive, and it can be difficult, right? Because of just the nature of the systems and the fact that they have to maintain availability. And this is kind of an old case study, but I think it's an interesting scenario, is that there's been a report in this paper I was reading where these people went into a factory to do a ping sweep, and they were ping sweeping, and for whatever reason it caused this robot arm to swing around the factory, and it broke a bunch of stuff, and it ended up being about 50 grand worth of damages, right? And I guess the heart of this little allegory is that it's not easy to test these systems. We can't just come in with this traditional approach that we've had with traditional network and security and stuff like that. That there's a lot of other considerations because these systems have to keep running, right? So what we want to do is use simulation to address some of these testing issues, right? So if we can create a simulated environment, then we can test without having to worry about swinging robot arms or without having to worry about breaking real equipment, because if we break the simulation, then we can just restart the software, right? And this is not necessarily a new practice. Simulating SCADA systems has been done before. Carnegie Mellon has a SCADA sim system that's commonly used for training and modeling different kind of infrastructure systems, and they'll even sometimes use it to model things like denial of service attacks. But the thing about this system is it isn't really designed to fully explore cybersecurity. There are some kind of situational things where they're like, okay, we're going to train these people to see what it looks like when a denial of service attack comes on, but they don't have the full range of attacks and the full range of kind of considerations that a system you really want for cybersecurity would need. The other things, like some people have built kind of high-level models, whether they be mathematical or kind of structural, but they haven't really done a full scope where they have a physical process and they simulated controllers and simulated operators. So that's what these other works have kind of done. This Thomas Morris paper is an interesting one. These people are from Mississippi State University, and they've been working on trying to build simulations like we have, but theirs are fairly small scale. So what they have in their lab is they have like a water tower. It's got a controller, and they basically try and maintain, like, let's say 100 gallons of water in the tank. I can't remember the exact number, but then so the tank drains water, and then the controller turns off to let more water in, and then that's their physical thing that they have, and then they try and model that in a simulation, and then they add some. I think they actually have like Raspberry Pis with OpenPLC on them, but so they have this kind of simulation that they can validate, but it's super super small scale. It's basically just one thing. And they have like a conveyor belt, and they're trying to work on kind of getting virtualized, but we're really not there yet with a lot of systems. And this is another thing is physical test beds are pretty common. There's one in Illinois, there's one in Idaho, where they set up a bunch of PLCs and different devices, but they tend to be really expensive, and they tend to be kind of hard to build and hard to use. So where do these simulations fall short? So I talked about it a little bit, but basically, big one is fidelity and accuracy to the real world. So many of these architectures are developed by people like me who are computer scientists, and they don't have the full engineering perspectives. What that means is that we design a lot of really cool, fancy stuff, but it might not be realistic, and we might not know where it falls short in terms of accuracy. Simulations also will not consider the full scope of cyber attacks that you might want for studying cybersecurity and ICS systems. So a lot of people will study denial of service attacks. A lot of people will study network-based attacks. But there's not very much work that actually looks into the control loop and the feedback, so the whole process of PLCs reading from a sensor, making some decisions, and then writing back to an actuator is kind of just not really existent in the literature right now. And I think part of that comes from the fact that a lot of people who work on these models are computer scientists who are really interested in the network security side, but don't have necessarily the knowledge to explore some of this kind of control loop side. And that's where it's useful to kind of be able to collaborate with engineers and stuff. Then a lot of these systems lack modularity. So they might be designed to simulate a specific thing or simulate a specific physical model. So that paper I was talking about with the Mississippi people, right? Their simulation is built to model this water tower, and that's what it does. But it's not really extensible past that. And they don't really integrate existing technologies very well. So some people will use Simulink, but it's fairly uncommon. And they're not really designed to swap in and out of these simulators, which is what we'll kind of talk about later on in this presentation about integrating existing technologies to make these simulations better. And the other thing is that a lot of these things don't have an extensible design that can allow hybrid PLCs, real PLCs, and virtual PLCs. So they might have one or the other, but they're not really able to do all of them. And there's actually a lot of value to being able to virtualize some of your PLC behavior and have some of them be real and have some of them be somewhere in between. And that has to do kind of with the cost associated with acquiring equipment, and also the ease of use that you can kind of get out of making your own virtual replicas of that equipment that you've acquired, right? And then previous literature also has not really investigated gas systems. So a lot of work has been done studying electrical systems and trying to simulate them or trying to build test beds for them. But gas systems actually can play a very large role in kind of our daily lives, right? Whether it's our water heater or our furnace in our house, and also, supplying gas to electrical power plants. And this is something that hasn't really been researched much in the prior literature. So that's why a large focus of our work has been in simulating gas systems, is because it's something that hasn't really been looked into in the prior literature. Okay, so why build another simulator? So where do we fit into this kind of whole scope of things? Well, we're trying to design and architect a simulator from the ground up, and we're trying to make it as modular as possible. And what that means is that we want to be able to integrate different physical simulators. So when I say a physical simulator, there's software out there, like the MATLAB software Simulink, or there's a software called PowerWorld. There's one called OpenDSS, I think, where these are kind of built by engineers or really smart people to model these types of systems very accurately using these mathematical models. And we want to be able to leverage that existing technology. So instead of having to go and write our own simulations, leverage the simulations that already exist and integrate those into kind of a cybersecurity environment. So we want to be able to integrate different physical simulators. We want to be able to take real PLCs that we can acquire if we get funding, or build our own kind of PLCs out of software, and then also integrate different HMIs so that we kind of have this simulation where we can change parts in and out in order to kind of get what we want. So maybe Simulink is good for a gas system, but maybe there's a better simulator for electrical system, let's say. So maybe if you can swap those out, you can kind of do different simulations that way. Or maybe you acquired some new PLCs and now you had an experiment you were running. Now you want to see what it looks like with this new technology in there. Or maybe you were running an experiment and you want to look at, okay, this company like General Electric has an HMI that they support, and maybe you want to test that HMI with your kind of simulation, or maybe you want to train people on that HMI and use the simulation as a backend. So that's why we want to design it to be modular so we can kind of meet all these different demands, right? And then again, we want to be able to, in the same kind of scope, we want to be able to integrate different SCADA network protocols. So the primary one we use in our simulation is called Modbus, which is an older protocol that's been around in industrial control systems for quite a long time. But there's a kind of new kid on the block protocol called DNP3 that's very popular and is gaining traction. And so what we want to do is be able to kind of swap these network protocols in and out to see kind of, okay, what happens if you were to add encryption to Modbus, or what happens if you use DNP3 and someone tries this kind of attack on the DNP3 protocol. So kind of things like that, right? And then finally, and I think most importantly, and why I'm grateful that, for example, like Dan is here, is that consulting with engineers, people like Dan and people at the Powerhouse, people like Sule, and then cybersecurity experts like Dr. Ray and Dr. Gersh, people who have the knowledge of the cybersecurity, bringing those kind of two groups of people together is super, super important when you're designing these systems, right? So figuring out which kind of cybersecurity attacks and cybersecurity concerns should we be looking at, but then also figuring out, okay, from the engineering experts, what happens to these physical systems if we were to do this attack hypothetically, and trying to figure that out, figure out what's important, what we need to be modeling, and then kind of integrating that into our kind of technology that we're using to study these systems. Okay, so we went a lot over what we aim to do and kind of the motivation for how we've got here. So before we dive into the design of our system, I want to talk about kind of these important considerations, and we've kind of gone over it a little bit in the goals of our system, but just to kind of make it a little bit more clear. So this is something I talked about, so I'm just going to skim over this slide, but integrating with existing technology, right? So in our model, we use the MATLAB Simulink stack, which is basically, it's kind of like a block-based language that can be used to model almost any physical system that you could model with math. So in the Simulink tutorial, they have you modeling like a bird diving out of the sky and then opening its wings, creating drag. And so that's a system of kind of equations and stuff, right? In the same way, gas systems can kind of be modeled with these kind of complex mathematics and stuff. But also the value we saw in using this type of Simulink software was that it's not limited to just gas systems, but in future iterations of the project, if we wanted to do like an electrical grid, or even simulate like a manufacturing center, or even possibly like integrate this somehow with the heavy vehicle security work, it might be possible to use Simulink as a simulator for that backend. So some other important considerations is validation methodologies, and this is something that Dan and I were talking about before the presentation, but how do we figure out that what we're doing is, like, especially from the physical modeling side, how do we know that it's realistic, right? And there's a lot of different strategies kind of to approach this problem. So you could use kind of different types of modeling, mathematics, right? And go, okay, the math makes sense, right? It works out. One way you could do it, and what I was talking about, is you could model a real system. So you could say, okay, here's this real system. We have data on this system. We're going to try and make a replica in simulation. And then what you do is you compare the data that kind of comes out of your simulation with the data that is in the real world, and then you could even compare the packet captures coming from your simulated controllers to packet captures from real controllers, and kind of using some sort of clever diagnostics and measurements of kind of distance of those two kind of data sets, you could kind of determine how close you are to the actual thing. The downside to this approach would be that you couldn't take the real system and put it into kind of a sketchy state, right? So with your simulation, you can cyber attack it, and you can say what would happen if all these gas systems suddenly lost a bunch of pressure. You couldn't compare that situation to the real system, because you're never going to want to put the real system in kind of that kind of state that could cause harm to it, right? So where we are right now in our work is that we mostly just consult with the experts around us, or at least I do, to try and figure out how far off we are, and if we're in the ballpark of how a real system would actually act. Then scaling simulation infrastructures is the next consideration. So simulation really gets useful the larger you can make it in some respects. So like there's an East Coast blackout that happened a few years ago, where stuff happening in Ohio and kind of power lines going down caused power outages in New York and in Canada and all over the place. And like I said, previous work has been pretty small scale, and if you can find ways to scale these simulations up to be extremely large, then you can start to study these kind of interdependencies that happen between these systems, right? And so this is a super important consideration, and something that we haven't fully covered. So our models have like probably 20 to 25 controllers in them, and we do have a model that's a rough scale, kind of medium sized, but we don't have something on the order of thousands, which is where we would like to get. And there's a lot of considerations for how you do that in a computationally efficient manner. So you either need a really powerful computer, or you need to do some kind of clever tricks to kind of model. Let's say you can model 200 controllers in a very simplistic way instead of having to model them in depth, and then that would allow you to kind of focus on in depth in other areas, right? So there's kind of tricks that you could do to kind of scale these things up, and that's kind of a future direction of our work, but it's still a really important consideration for making these simulations valuable in the long term. Okay. Simulating long-term system behavior. So what this means is, like in electrical systems, things can happen really fast. So, a transformer could go offline, or a power line could go down, and that could cause a failure within minutes. But with our gas pipelines, because they're physically moving gas in the simulation, right, and that takes time, and it's a lot slower. And as a result, if we were to run these simulations in real time, we would be trying to study the behavior of something occurring over 2 or 3 days. In real time, it's just not very useful. So what we want to do is be able to kind of speed that up and simulate those 2 or 3 days in a few minutes, and then be able to kind of explore the results in depth. However, when you speed this simulation up, it can kind of lead to other issues, and that's something that we can talk about kind of later on in this presentation. Then integrating hardware in the loop. So I talked about this a little bit earlier on, but you want to be able to actually get some real hardware in there. So right now we're almost entirely virtual, but we're working hopefully at some point in the future to get some real hardware hooked up into our simulation system, because a lot of the literature and the surveys on kind of this simulation stuff have kind of found that when you integrate your kind of virtual PLCs with your real PLCs with your simulation, that's kind of when you get the best of both worlds. So you get the accuracy of these real PLCs, but you also get kind of the cost efficient and cost effectiveness and the ability to scale that you get from kind of creating virtual models of real things, right? So this is still a work in progress for us, but it's something that we'll hopefully have out in the future. And then finally, the last consideration in this list is network simulation. So our simulation is a fairly rudimentary to SCADA network, but what we will be working towards eventually is being able to model several different network architectures. So why this is important is because network-based attacks, denial of service is just one network-based attacks, and there's all sorts of protocols that exist, right, in computer networking that have their own unique vulnerabilities. And in addition to this, because these systems can kind of scale over large geographical areas, it's possible that you have certain delays that are introduced in a real system that we're not really able to model because we're not able to delay the network traffic, right? We just have things kind of occurring as they occur. But we would want to be able to kind of model that behavior of like, okay, when you send a packet from, let's say, from Denver to some, controller in the Fort Collins area for whatever reason, there's going to be some sort of round-trip delay that occurs between the decisions you're making in Denver and the behavior that's occurring in Fort Collins, let's say. And that's something that is useful to model. Okay, so where our simulation is at in terms of cybersecurity, mainly what the types of attacks we're able to model right now. We can model measurement attacks, which is something I'm going to talk about in the next few slides. Command injection, which is kind of like when you send false commands to a controller, and then other kind of attacks that are based around this kind of control loop stuff I was talking about. And then in the future, we're not there now, but we hope that we could eventually start to model things like ransomware, things like denial of service, network-based attacks, malware, and worm propagation, data exfiltration, all these other things that happen in these systems and happen fairly commonly. Being able to kind of add that to our stack of, let's say, just kind of attacks that we can study and simulate is definitely a future direction. So what is a measurement attack? So a core part of my work in my thesis talks about these measurement attacks and studies them. So a measurement attack kind of works by compromising the feedback that you get in this control loop. So down here, I don't know if you guys can see my mouse, but basically we have this controller, right? And this mu on the left is some set point. So this is kind of the ideal state that you want. Mu prime is the reading that you're getting out of the physical system, and then you have some function that takes into account the difference of the ideal state mu and the current state mu prime and makes an adjustment based on that. So I think the best example I can give is a thermostat. So your thermostat, right, has a thermometer on it, and the thermometer determines the temperature in your house, and then the thermostat adjusts the heat or the AC or whatever based on that, right? So in this scenario, right, you have a desired temperature. You want to keep your house at 70 degrees, and then your thermometer might read 65, so it turns on the heat, and that 65 would be your mu prime. So what a measurement attack is like, let's say that it's a cold day, it's 40 degrees out, right, in your house, and your thermostat isn't turning on. It's not heating your house. So what's happening? Well, what's happening is, let's say that the thermometer on your thermostat is broken or it's being tampered with or something. So what's happening is it's reading that the temperature in your house is 75 degrees, even though the temperature is 40 degrees. And so as a result, your desired temperature is 70, and it reads this difference and says, oh, because the only way your thermostat knows about the world is through this thermometer, it thinks that everything's fine even though everything's not. So it's kind of like on your thermostat, if it was falsely reading too low, then your heat would always be on because it would always think your house is colder than it is, right? But if it was falsely reading too high, then your heat might never come on because your thermostat might always think that your house is warm even though it's freezing cold. And so this seems kind of like a funny and contrived example, but I was reading an article online on Lifehacker of people doing this in their office, which I think is pretty funny. When like in the winter, when they'd keep the temperature low, people would put an ice pack on top of the thermostat, and this would actually cause it to heat up their office. So I thought that was kind of a funny example. But the main kind of point to take out of here and why we want to study this is if you can manipulate a sensor or some set of sensors, it could be possible for you to change the behavior of the controllers in the system. And that's kind of the main point that I'm trying to make. So before we go into all these experiments and stuff, I'm going to talk about the design of the simulation that we have built and the one that we've been using to run the experiments that we're running, and then we'll talk about measurement attacks kind of on the simulation. We'll talk about the models we built in our simulation and then the measurement attacks we've done on them. So The critical parts of our design are this kind of 3-layer architecture that we've come up with. And this is a lot of work that Jerry, Duggan, and I have worked on together for the past couple years of kind of developing that. And then being able to interface with Simulink and Simscape, which is a library kind of extension of Simulink. Finding ways to create realistic gas pipeline models. Resolving timing issues when we start to simulate, a week over 3 minutes. Simulating compromises in the system, and then using something we call an Oracle PLC to get out the authentic data even when we are doing measurement attacks. So to start with, the way that we have this simulation kind of laid out is in this kind of 3-layer stack. So at the bottom layer, we have our physical process model. So that is our Simulink MATLAB simulation. And what this does is it models the dynamics of the gas system. So it models the mass flow and the temperature and the pressure and everything occurring in the system. And it's basically chugs away and solves a bunch of equations. And then on top of that, in this second layer, we have basically what we call this would be the kind of control layer in an ICS system. We have what we have built called our Simulink interface, which is a piece of software that allows us to kind of plug in to this Simulink model and then create virtual controllers that we can kind of interact with this Simulink model with. So we do that using some UDP data channels to send data in and out of the model using these kind of network blocks that are provided by Simulink. And then the Simulink interface works as kind of a mechanism that distributes that data amongst these different PLCs. And then the PLCs can either make decisions themselves about things occurring in the simulation, or they act as Modbus servers. So typically something like a PLC will have what is called a Modbus server, and this will interact with the final and third layer, which is the human-machine interface. So what will happen is, like, if someone's sitting at a control center, let's say in Houston monitoring the gas pipeline, what that control software is doing is it's sending network requests to these different PLCs and figuring out, reading the data that they have. So the PLC reads something from a sensor and stores it in a register, and then there's a software that requests the data from that register using the Modbus protocol. So what we have here is kind of our physical process, our control layer, and then our human layer. And between the kind of human operator layer and the control layer is where our SCADA network is. Okay, so how does this interface work? So I talked about how it uses kind of UDP network blocks to get data in and out of the Simulink process simulation. So what it's really doing is this Simulink interface is basically kind of a publish-subscribe mechanism, but it's what is it called? It's a server that it's a single-threaded server that uses select. So what it does is when you are creating a bunch of virtual PLCs, they each register themselves to the select server and say, hey, I'm listening for data that's coming out of the simulation on this channel. And then the Simulink interface is what it does is it basically fires up a bunch of servers to listen for that data coming out of the simulation. And then it dispatches data to each one of these workers, each one of these workers. So what's happening is this Simulink interface gets data, it puts it on a queue, that data gets popped off of a queue, and that worker reads the data, and it updates the state of the system within this kind of virtual PLC. And then if you want to respond back through the interface, what you do is there's a specification for it in the configuration files. And so what happens is there's a pipe that's created between the Simulink interface and the actual virtual PLC. And the reason that we did this is because it's so that basically, since this thing is a select server, it's able to monitor response data and data coming from the Simulink interface on the same thread without having to do a bunch of basically multi-threading and multi-process stuff. So that just kind of simplifies the design, but it's not kind of totally, it doesn't have to totally be tethered. So when we go to build when we go to integrate an actual PLC into the system, we'll be able to either come up with ways to kind of have that communicate back through the interface, whether that be through creating kind of like a process that talks to this physical controller and then kind of converts that to a digital signal that can be sent back through the simulation, something like that. So then talked about some kind of how this interface is on a high level. How do we simulate these measurement attacks and these compromises? Well, what we do is up here on the top of this diagram, we have our standard kind of worker thread. And so, like I said, the worker thread, it basically reads data from the Simulink interface. And when this PLC requests to get a reading from that worker, it'll respond with the reading. So these workers are kind of just like these threads that all they do is deal with handling a specific sensor reading, right? So what happens is when you want to simulate a measurement attack or a compromise, we basically just add this compromise layer between this worker and the virtual PLC. So when you go to get the reading, instead of responding, let's say if the reading is some value X, we model this kind of measurement attack or this compromise as a function of the original reading X and time, which is T. So what we can do then is we can use kind of this kind of functional definition to apply different measurement attacks. So let's say that we want this sensor, let's say it's a pressure sensor in the system, we want it to show a steady decline over time. So what we do is we design this compromise layer to be some decreasing function with respect to time and with respect to the original input reading. And then what happens is when we go to pull this reading, the original reading is modified by whatever this function is, and then it's returned to the virtual PLC. So then these PLCs are talking to the Simulink interface, right? There's some compromised data that's being extracted out when the Modbus servers are queried. So then what happens when we're running these simulations, okay, and we have the compromises set up, we're doing these measurement attacks. How do we differentiate which data is the real data from which data is the fake data? And what we do is we use something called an Oracle PLC. And all this Oracle PLC really is it's another virtual PLC, but it's solely responsible for collecting data that is kind of authentic. So because the compromises are specified within the kind of virtual PLC, what we can do is we can create another kind of replica and assign it all those workers that we're compromising in our configuration. And then that Oracle PLC will be our source of ground truth data. And this is really important because then it allows us kind of when the simulation is over to compare the lie data to the real data and kind of see the disparity between the two. And we'll see that when we kind of look through the experiments. Okay, so the Oracle PLC also has an important responsibility, and it has to do with propagating time. So, like I said, we want to be able to speed the simulation up, right? So we want to be able to run 3 or 4 days in the course of a few minutes. Well, if we want to do that, we need to have some way of informing the rest of our kind of simulation stack of what's going on, right? Because simulation time is something that is only really it's only really known to Simulink, right? Simulink has its sense of the simulated world, but we need to find a way to kind of propagate that sense of time throughout the whole system. So the way that we do this is that every time we export a reading out of the Simulink process, we're also pushing a timestamp along with it. And so every sensor reading has a timestamp that accompanies it, and then each time one of these workers within the PLC basically gets a new sensor reading, it also updates its current kind of clock so that it knows what the current simulation time is. And then what happens is the Oracle PLC, it is able to actually, if you send it a certain Modbus request, it'll send you back the current simulation time. And so in that way, kind of the HMI or the whatever we're using to model a human operator has a sense of what the current time is in simulation time. So in this way, we can at least get everyone informed about the time, but it has a kind of crucial flaw in the sense that the virtual PLCs and the kind of operator and front end are always playing catch up to the simulation. So the simulation is spitting out sensor readings and spitting out time, but it's not slowing down for anything else. So what happens is, like in the standard kind of control loop, the simulation sends a sensor reading out that goes to the PLC's Modbus queried, and then there's some decision made and it kind of goes back through that whole infrastructure. And any delay that's caused between when the reading came out of the Simulink model and between when the next kind of command came in any delay in network communication or software or anything is magnified because the simulation is running so much faster than real time. So what could happen is, like, let's say that every one real world second is 500 simulated seconds for the sake of argument. That means that if there was a 1 second delay in our system, which there's not, but if there were, then that would mean that we had missed 500 seconds of 500 seconds of the simulation had advanced without any control or without any kind of interaction. And so this is kind of something that is a very difficult problem to solve, and it involves kind of finding a way to kind of synchronize everything, which is possible, but we just haven't got to it in our software yet. But it's a kind of an important thing to think about that can lead to certain inaccuracies. Okay, and then modeling the gas pipelines. So this is something that basically my work has been equal parts building this Simulink interface and equal parts kind of modeling these gas systems. And it can be very challenging to model these things in a realistic fashion, right? So the pipes must be sized to the proper size to deliver the amount of gas they need to deliver. The gas demands need to be realistic for the type of system that they're in, right? And then the compressors need to be designed in such a way that they're compressing gas in a fashion that kind of makes sense and that they're not using too much power and stuff like this. But most of that work has been done by consulting with people like Dan and by working with Jerry and by kind of trying to figure out how we can make these simulations as good as they can be for what we're trying to do. So in addition to modeling the gas systems, there's also this process of modeling the operators of the system. So people who would be sitting behind a desk, watching a human-machine interface and making decisions about the state of the system and maybe making some control adjustments. So mainly with our control model, we, at least in experiment 1, we use kind of this approach where we look at the downstream power plants and compressors and we update the pressure inputs into the system based on that kind of disparity. In our more advanced simulation, we use kind of an approach where so like these compressors have a power limit on them, right? So it requires energy to compress gas. And if that energy is exceeded, basically the compressor is only going to compress as much as it's able to for that given amount of power it's supplied. So what we do for our kind of more advanced model is we adjust the amount of power we're supplying to the compressor to allow it to compress more gas. And then we also, in our system, want to model scenarios like low pressure and temperature shutoffs. And this is actually something that's done in the simulation now. But basically, with these systems, if the pressure gets too low, then there's not enough gas being supplied to a power plant or something like that. It's just not able to run. If the temperature drops too rapidly, what can actually happen is the gas can freeze. There's something called a dew point with this gas, and I'm not a complete expert on it, but basically it can become kind of like, as Dan's described it to me, kind of like shotgun pellets floating through these pipes, right? And so this can cause damage to the system. So a lot of times, if the temperature starts to drop that rapidly, they'll shut these things off before it ever gets to that point. So modeling these operators is kind of the third part of the kind of modeling thing that we're doing, right? So we're going to move on to our kind of example models and look at our experiments now. So the first thing is kind of our small scale model, and this is kind of just get us oriented, kind of demonstrate a basic measurement attack, and then we'll move on to our little bit more sophisticated model. So what we have here is kind of a basic model. It's got a single compressor, it's got 2 lengths of pipe, and it's got a simulated power plant. It's got some sensors and some actuators. And so kind of the control for this model is we have kind of a piece of software that's reading this pressure value that's coming out of the system, and it's adjusting this input setting for the compressor. And in this system, for the kind of sake of example, the process of this power plant tripping off is not actually in the physical model, but it's on the control side. So the controller can be told to trip the thing off. So it allows the operator of the system to turn power plants off if they're becoming in a state that might be dangerous. So what happens with a measurement attack in this system is, what we do is, actually let me go back, is we take this this pressure reading here and we lie about it. We have it gradually decrease over time. And so what this does is eventually it gets to the point where the power plant is going to trip off, but it also causes the operator to make adjustments based on false information. So here is kind of, this green line is the actual pressure at the power plant. The blue line is the compromised reading. So this is kind of the sensor that we're lying, and we're having it decrease over time. And then this orange line is temperature for reference. So we can see that as this kind of pressure reading falls in our compromise, we can see that the real plant pressure is going up. So why is this happening? Well, what's happening is the operator of the system thinks that the pressure is low here. As a result, that person is adjusting the pressure up here and increasing that kind of output of the compressor in hopes to kind of compensate for this loss. But in reality, there was no loss in the first place. This is just a faulty sensor, right? So what this causes is for the pressure in the system to increase. And then what happens down here is kind of like the power plant, I think, trips off somewhere around this point. But I think it's also important to note, and I think it's interesting, that it's something we'll talk about in the future work section, but you can see that even though we're lying about the pressure, we know that the real this is the temperature reading that is being received by the operator. The temperature isn't changing too dramatically. So normally if you'd see kind of this change in pressure, you would also see some change in temperature associated with it because of gas laws. And this is something that you could leverage in a kind of scenario where you're trying to defend against these attacks. And that's something we'll talk about later on. But basically the kind of idea here is to kind of get us oriented with what the basic nature of what this kind of attack would look like. The problem with this, right, is this small scale model is kind of uninspiring for, oops, sorry for going back too many. It's kind of uninspiring for demonstrating these types of attacks, right? So what we want to do, and what we have done, is create a larger model that's a little bit more sophisticated to truly kind of try and show the impacts of these attacks in a more realistic manner, right? So for this reason, we designed, I call it the Colorado gas model, but really what it is it's a model that's kind of inspired by the Colorado Front Range gas system. Using this model, we're able to kind of demonstrate measurement attacks in a more kind of interdependent system than just this kind of single power plant, single compressor scenario. So how did we kind of design this model, and what did we go through? Well, kind of the primary objective of designing this system wasn't necessarily to be a perfect replica of the Colorado gas system, although that could be a possible kind of future scenario now that we have some of the data that we didn't have before. But the main goal is that we want this model to be realistic enough that it fails because of these cyber attacks we're testing on it and not because it's designed poorly. So for reference, our system, the model that we have is about 12 pipe segments, and if you were to sum those up, it's about 1,256 miles of gas pipe. There's 9 loads in the system. 3 of them are distribution loads, like for your, water heater and that kind of stuff, and then 6 of them are simulated power plants. The total capacity of these 6 simulated power plants is about 2,900 megawatts, and then there are 8 compressor stations kind of through these gas lines. So how do we design this model to be realistic? Well, for figuring out the locations of where compressor stations might be, and for looking at the length of the pipe and the distance of the pipe, what we did is we took this system map from Kinder Morgan, which is up here on the left, and we overlaid that on a map of Colorado, and then we kind of basically, we looked at this and we said, okay, like that looks like, Fort Collins, and that looks like Longmont, and there's Denver, right? And then we kind of look at these red things are gas lines, and then these little stubs likely indicate either a power plant or gas storage or kind of some sort of leaf node of this kind of tree, so to speak, right? So we kind of overlaid that on a map of Colorado, figured out where we think power plants might be, where major cities are, where compressors might be, and then we kind of used some Google mapping to figure out the distances and stuff. And then once we had that figured out, we needed to determine how big these power plants needed to be so that we could design kind of realistic gas loads. So what we did is we looked at Xcel Energy at some of the natural gas stations. And so, for example, here on the right is the Cherokee station in Denver. And this station has a capacity of about 930 megawatts. And so what we did is we said, okay, 930 megawatts, how much gas is required to generate that much power? Well, we used some math using the heating value of natural gas and the efficiency of the power plant, and we were able to determine that, say, for example, a 400 megawatt power plant will require 58.79 kilograms per second of natural gas being supplied in order to generate that much power. So once we had kind of figured out how much gas each power plant would need in order to generate some amount of power, so we assigned power plant capacities to each plant. So the Denver one, we gave it like 950 megawatt output, and then some of the smaller ones were more like 400 or 500. We figured out how much gas was needed for each of those power plants to run at that max capacity, and then we determined how big the pipes need to be in order to deliver that much gas to those power plants. So what we would do is say, okay, this is a lot of the engineering of the model, but what does the diameter of the gas pipe need to be in order to deliver that much gas? So for example, in this table, if we needed 30 kilograms per second of gas, the diameter of the pipe would have to be 16 inches, right? And so we did a lot of little math to kind of figure out, based on our limited knowledge. So we know that the power plants can be about this size. We know that they might be in these locations. We use that limited knowledge to kind of extrapolate and figure out how big the pipes need to be, how long they need to be, and where they need to be. Okay. So once we had designed the model kind of based on that information, we needed a scenario that we could use. And so the scenario that we kind of looked at is that in some places of the world, and this is actually becoming more common, is that wind farms can carry a large amount of the power load. And so what will happen is, and this is something that's happened in the past. I know it was somewhere in Europe, and Dan was telling me about it, but it's possible for these systems to be carrying a very high load, right? And then what will happen, or what can happen, is that the wind can die down either really fast or something can go offline. And as a result, all of a sudden the natural gas system has to pick up the slack. And so the system has to ramp up. More gas has to be pushed through the gas lines, and manual operators might have to intervene in order to make sure that all the gas doesn't just totally get evacuated out of the system, but that everything is kind of up and running in order to meet this new demand. So what it looks like, this is a figure from my thesis dissertation document, but so we'd have like kind of a nominal load on our kind of gas generating power plants, and then here our wind farms go offline, and our load spikes up very dramatically for about 12 hours, and then something like everyone goes to bed, or they're able to get the wind farms back up, and it kind of drops back down. And so this top chart is what it looks like this is actually from our simulation, what it looks like when there is an intervention from the controller. So the operators, basically they let those compressors kind of go into overdrive and turn on to higher power in order to meet this demand. And then this bottom chart right here is what the system looks like if you don't ramp the compressors up to meet that new demand. And so what happens is it makes it kind of towards the end of this 12-hour window, and then it just starts to drop off. And this is because there is storage in these pipes, so it's able to survive for a little bit without any more gas being put into the system, but eventually everything just kind of breaks down. And so what we have here is near the end of this 12-hour window, if there's no control intervention, we see that a few plants start to go offline because they're not being delivered enough gas. And right here, this looks like a loss of, I know it's kind of hard to see in this figure, but this is 2750 and this is 1500. So that's a loss of over, I think, 1200 megawatts of power if there's no intervention, let's say, right? And this occurs, so this is actually a zoom in. So the x-axis isn't the best, but this occurs over a few minutes, if you could read those points a little bit more clearly. So the idea here is, if you're a smart attacker, you can sit on the system and wait for one of these scenarios where it's under a lot of stress, and then precisely as the system has to ramp up, that's when you start your attacks and start to try and basically start lying about some of the sensor readings, start trying to kind of get things to oscillate, get things to trip off, and maybe even cause some cascading failures in order to kind of take this system down. So what you're doing is you're waiting till it's, I guess, most vulnerable, so to speak, and then that's when you're going to attack, right? And so for our scenario that we're modeling, we're going to do some measurement attacks on it, and kind of this kind of operational definition we've set up is a successful attack will have to cause some plants to fail within this window, right? Because this is when the system is most vulnerable. So what is the kind of first experiments we run on this system? We call them kind of single point of failure attacks. So what we do is for